Two announcements before we get going concerning just our somewhat strange schedule for the next week or so. We are not having class on Tuesday, as I mentioned last time. We are going to have homework due, though. I would like it to be due as usual on Wednesday, although I think I'm not really allowed to make something due on Wednesday because that's during the break. So I'm going to say, if the dean asks you or whatever, the homework is due Tuesday. That's a day early. But if you want to do it on Wednesday, that's totally fine with me. Just don't forget to do it before you leave for the break. So I'm going to say the next homework assignment is due on Tuesday, the 25th, I think, is the date of Tuesday. But if you want to do it on Wednesday, that's totally fine with me. I'm not going to grade it on Tuesday probably, so hand it down on Wednesday as usual if you like. The quiz, though, I would like to do the quiz. We're not meeting on Tuesday of next week. We will meet all 3 days the following week after the break. I would like to do this quiz on Tuesday after the break. So this will be quiz number 10. Number 9 was today. Quiz number 10 on Tuesday after the break. This will just give you one more shot at the stuff that's on the homework rather than just including it. That Friday is going to be our last test. So Tuesday after break. All right. So, and this homework will be based on that, or this quiz will be based on that homework assignment. All right. And then, of course, the Friday after break is our last day, and that's our last in-class test. All right. I hope that's clear to everybody. Great. Let's talk some more about power series then. All right. So last time we just sort of started this a little bit. We are talking about the power series of a function. And we started with one basic example, and that's this. 1 over 1 minus x has the power series of just x to the n equals 0 to infinity. And this converges when absolute value x is less than 1. All right? So this is kind of like our starting point, and then today we're going to talk about simple variations of this and eventually getting to sort of like not so simple variations. Actually, you can get pretty far just by looking at variations of this one series like that, all right? It converges when the absolute value of x is less than 1. And last time we did just a real quick example of what about 1 over 1 minus 2x? You can get a series for that by just plugging in 2x instead of x into the one that is written right there. And so this would look like 2x to the n, which if you like you could simplify to 2 to the n, x to the n, right? I actually prefer to write it this way. Usually when I write a power series, I want to see some coefficient times some power of x. And so I like to write it this way rather than this, which is, they're the same. But I like to see coefficient times x to some power, and that's that. And this one converges when, again, I just plug in 2x, so 2x less than 1. I don't really like that way of writing it, but you can just divide by 2, and it says that, all right? So this is the interval of convergence would be interval -1/2 to 1/2. And if you like the radius of convergence, it is 1/2. That's the radius of convergence. All right? So let's talk about some fancier other tricks, slightly fancier tricks. Of course, you could, rather than saying minus 2x, you could put any constant here that you like, and it's the same idea there. What about, anybody want to give me an idea? You can do this with a plus using a simple trick. Anyone have a suggestion here? Based on this one here works when it's a minus. What if I want it to be a plus? Yeah, you could think of this is the same as this with a negative x plugged instead of x. So if you like, what I'm imagining is really that's like that. And then I plug that into the one up top using minus x instead of x. So this will be the sum minus x to the n. And as before, I like to write it as some coefficients times some power of x. And so I will split that up just like I did with the 2's, like so. Minus 1 to the n, x to the n. So this is an alternating series now. Minus 1 to the n, x to the n. All right. And when does this converge? We're always going to talk about what is the series, first of all, and then also what is the convergence. So this one converges when, again, I'm plugging into the standard example, which is at the top, but what I'm plugging in is minus x instead of x. This is a bit of a anticlimactic. It converges when absolute value negative x is less than 1, but that's just the same as x, absolute value of x less than 1. So not terribly interesting convergence, but it's the same interval of convergence as the one up at the top there. All right. Okay, how about let's get increasingly fancier with the tricks. How about this? 2 minus x instead of 1 minus x. Maybe I'll just copy this guy. This is the one we're going to be sort of like inspired by the whole time. Put that one in a box somewhere. Anybody want to suggest another simple trick that I could do to make a 2 there? This is a little trickier. And maybe there's more than one way to do this, but I have a particular way in mind. Any ideas? It's actually a similar trick that we did. This was a while ago when we were talking about inverse trig functions. We did something like 4 plus x squared. This is basically like an arctan, but the arctan, you need a 1 here. Anyone remember how we compensate? Like instead of a 4, I wanted to see a 1 here, so there's a standard little trick. Yeah.
Divide by 2 equals the whole term.
Yeah, here, like over here, I would just divide everything out by 4, which turns that into a 1. It messes up the x squared, but we can handle that by other means. And the same idea over here. I'm going to divide out everything by a 2. So that is, I basically am going to pull out a 1/2, and it becomes that, right? I'm factoring a 2 out of the bottom everywhere, which is why the 2 becomes a 1, and also the x has to become a x over 2, because I factored the 2 out of the whole bottom. And now we plug into the formula on the side there. Maybe I'll put this in a box. Now I plug into the formula in the box using x over 2 instead of x. So this now becomes, and you just have to leave this 1/2 outside, but that's, I'm all right with that. Plugging into the box using x over 2 instead of x. So it's this, right? And then again, as usual, I like to write this as something times the power of x. So I'm going to do the nth power on the top and the bottom. It says 1/2 the sum x to the n over 2 to the n. And then, just for fun, I'm going to put the 1/2 back in. You can sort of, a constant can move through a summation sign. That's really the distributive property. So this is the same as a single power series. It would be this, 2 to the n plus 1. Because there's 2 to the n here, but then I'm putting another 2 down there. That means instead of, originally there's n factors of 2 here. Now there's an extra 1, so it's now 2 to the n plus 1 on the bottom. All right. This is yet another simple trick for dealing with these series. And let's talk about the convergence here. Converges when you have to remember exactly what did I plug in here. I plugged in x over 2. So the convergence will say x over 2 less than 1. All right, that's because x over 2 is the thing that I used when I turned it into a series. And then this I would solve for absolute value x by multiplying the 2. Absolute value x is less than 2. That's the radius of convergence is 2. Or the interval, if you like, would be -2 to 2. All right, this is yet another simple trick. All right, I got a couple more simple tricks. They get, gradually less simple. How about this? X over 3 minus x. This time I have an x on the top. It's, it was usually a 1 on the top, but I got an x this time. I think we can handle it. Even so, I'll bring this guy down. that thing in the box you basically need to have memorized. So that, like every example that we're doing, at least for now, is based on that. So hopefully you can remember okay. Anybody want to suggest tricks to do on this one? I would say you need some kind of a combination of two different things. You could suggest one of the things if you like, or both of the things. What do you think? Are you mystified by my wonderful scarf? It's a little hot in here, actually. I'm already committed, though. I can't take the scarf off now. I'm in too deep. What do you think? I would say we got the 3 on the bottom to deal with and also the x on top. I think we can handle the 3 in the same way as we did in the previous example. Just take 3 out of, really, it looks like a 1/3 when you pull a 3 out of the bottom. It's like so, right? What about the x up top? Any idea? What do you think?
Can you treat x like a constant? Pull it out and then
Yeah.
kind of treat it like the 1/3.
Mm-hmm. Yeah, this is not really an especially fancy trick here. You can also just pull the x out. I mean, at this point, all I'm talking about is just like ordinary multiplications of fractions. So, you might be wondering, like, am I allowed to move the x over here? Like, yeah. I mean, there's nothing else going on here. This is just multiplication. So yes, you are allowed to move the x over here. And then I'm going to turn this second part into the series. So I have x over 3 outside, and then I have that becomes the series, x over 3 to the n. As usual, I will split up the n there. So this is x over 3 times the sum x to the n over 3 to the n. And then finally, I'm going to like redistribute that part that's outside the sum, put it back inside the sum. And again, at this point you might feel a little weird. Am I allowed to bring x through the sum here? But the answer is yes. I mean, x is there's nothing special about x here. This is a sum in terms of n. Like, you shouldn't bring an n inside and out because that doesn't make a lot of sense. But x is totally fine. So we put the 3 back in, and I get 3 to the n plus 1 on the bottom. And I put the x back in, and I get x to the n plus 1 at the top. All right, so this is the series. Really, the extra x up in the numerator is not a problem to deal with at all. All right, and then what about the convergence? It converges when, again, you look only at this part, the part that you actually used when you plugged into the series formula. It's x over 3. So this one converges when absolute value x over 3 is less than 1, which is to say absolute value x less than 3. All right. The other extra x doesn't affect this this convergence part. All right. All right. I got one more of these simple tricks, and then I have some for you to try. Really, I mean, they're all fairly straightforward in my opinion. How about this one? Is maybe the fanciest looking. How about that? X over 1 minus 2x squared. All right. Now the x up top is no big deal. You can just sort of take the x, bring it out here, right? And it's 1 over 1 minus 2x squared. What's weird about this one is we have 2x squared down there. I would like to see, my standard format is just 1 over 1 minus x. Here instead we have 1 over 1 minus 2x squared, but I mean, it's a little weird, but we can still just plug that into the original formula. So I'm plugging up here using, instead of x, I'm using 2x squared. So we get x out here is just because I had to factor that out. And then this becomes the sum 2x squared to the n. All right. We're using the formula in the box, but with 2x squared instead of x. And now just to clean up the summation inside there, I have x, the sum. Do the nth power on each one. That looks like 2 to the n and then x to the 2n, right? X squared to the n is the same as x to the 2n. And then we can put that x, which is on the outside, back inside. That gives me one additional factor of x on the inside. So it's 2 to the n, x to the 2n plus 1. And this is my series format. All right. This is kind of an interesting series, actually. If you were to write out the terms, it looks like, so starting with n equals 0 is what we, if you're using this formula right here, it always has to start with n equals 0. So if I write these terms out, the first one would be 2 to the 0, which is 1, and then x to the 1. So it looks like x. And then the next one is 2 to the 1, x to the 3. The next would be the next power of 2, x to the 5. So this is a series which includes only odd numbered powers of x. And then the coefficients are the powers of 2. This is interesting looking, in my opinion. Can we say, what about the convergence? Again, we just plug in here. This time this is a little strange, but 2x squared less than 1, right? It's always absolute value whatever less than 1, where the whatever is the part that you actually plugged into the series formula. And then this, I would like to kind of solve for x here, although it has to be always inside the absolute values. I can divide 2 first. 1/2 like that, right? X squared, the absolute value, is the same as absolute value of x squared, and then I can solve for that by taking the square root. So it's this. That's the radius of convergence is 1 over root 2. A little weird, but that's how we do it. All right, I got some like this for you to try. So these, once you know what's up, there's not a lot to it. You just have to kind of identify the appropriate simple trick to use. All right, each time your job is write the series and say when it converges. Then we'll talk about some less simple tricks. And I would like you to simplify the series so that it looks like that. Some coefficient times x to some power. Okay. You solve that for x.
Yeah.
All right here.
Yes, that's it.
Huh?
Oh, sorry. This is a plus though?
Like the standard form.
Oh, I see what you're saying.
Another little trick. Oh, man. Yeah, it's looking good. Okay. I'm going to start doing some of these. Looks like people are doing fine. All right, can we talk about these? They are just kind of this similar simple tricks for each one. So the first one, you have to pull the 3 off the top is no big deal. The 2 on the bottom is a little weird, but I'm going to pull 2 out of the bottom. That makes this 2 a 1, and that makes this x a x over 2. And I'm also going to compensate for this plus, I'm going to write it as a minus minus, so that when I turn it into a series, it's a minus x over 2 on the inside there. All right? And then, just to simplify this a little bit, I will write it as minus 1 to the n, x to the n over 2 to the n, and then push the 3 halves back in. It will say the sum minus 1 to the n times, I guess, 3x to the n over 2 to the n plus 1. Like that. I hope you got something like that. 2 times 2 to the n is 2 to the n plus 1. All right, and then the convergence here, the convergence is the thing that I plugged in was that being less than 1. And then just to solve this for x, first of all, the minus sign in here can just kind of disappear because it's inside the absolute value. And then I multiply the 2 across. It's that. That's the convergence domain. All right, I hope you got something like that. Okay, the second one you should pull the x squared out, and then maybe the second one is easier, I don't know. The second one you should sort of take the x squared out, and then I have 1 minus 3x, and then that one I can just plug directly into the formula that I hope you all have memorized by now. It is 3x to the n, like that. And then writing the 3 to the n, x to the n, and then put x squared back in, it should be 3 to the n, x to the n plus 2, I think. I hope you got that. And then the convergence here would be 3x, absolute value 3x less than 1, which is to say absolute value x less than 1/3. That's the radius of convergence. All right, I hope everybody's feeling good about these. And then the last one is another similar batch of tricks. The 2 up top, you just factor out the 2, and then I am going to write the rest of it as 1 over 1 minus negative x squared. And so this is 2, the series, negative x squared to the n. So this is 2 minus 1 to the n, x to the 2n. Right? I hope that's what you said. Minus 1 to the n times 2x to the 2n. All right? Any thoughts about that one? So this one, interesting, has only even powers of n, right? Because every power there, the first one is the first one is power 0, but then it's 2 and then 4 and then 6. This is only even powers of n. And then the convergence for here would be negative x squared in absolute value is less than 1. But this is all just the same as absolute value x less than 1, because you can do the absolute value on the square and then take the square root on both sides. It doesn't change anything. All right. Any thoughts about that one? I hope nobody minds, by the way. Anybody get nervous when I take the square root on both sides of an inequality? You should at least briefly ask yourself, is that allowed in an inequality? Do I got to change the direction when you do that? The answer is yes, it is allowed, and no, you don't got to change the direction. Although those are not really obvious facts, these are things that you should sort of think carefully about. The reason that it's okay with the square root is actually because the square root of x, its graph looks like this, and the square root is an increasing function, always increasing, which means if one thing is smaller than another thing, then the square root of the other thing is smaller than the square root of the other thing. This is true, but actually it's only true because the square root has this shape. So it is not generally true. With an inequality, you can't just do whatever you want on both sides and expect it to still be valid. But it turns out you can do an increasing function on both sides. Actually, you cannot do a decreasing function on both sides. Like if I wanted to do, say, 1 over x on both sides, actually that messes up the inequality. But square root is okay. And actually any nth root is okay. So if you ever have a power here, if it were like x cubed, and I want to do the cube root on both sides, actually that is allowed. But other different kinds of things on both sides, you should be concerned before trying it. All right? Okay. Excellent. Let's talk about some less simple tricks. I would put all of those in the category of sort of simple tricks. You could probably have come up with those tricks on your own if you really had to solve these problems for some reason. It's not all that difficult to come up with. Here is a less simple trick. This is something that actually is not so crazy to come up with on your own, but this is a fancier trick. And once I tell you the name of the trick, you will immediately know what it is. This is called, I'll write it as a theorem, because it's actually not obvious that this is valid, but I'm telling you it is valid, and I don't really want to go through the proof of this. But this is called, the name really says it all, term by term derivative and antiderivative. All right. It says, this is the statement of the theorem. This is a true fact about power series. It says if f of x has some kind of power series, Cn x to the n, so that is some constants times powers of x. And if this is a power series and f is continuous and differentiable, that is, you can take the derivative. This automatically means that also you can take the antiderivative. If this is the function power series and this is differentiable, then the power series for f prime of x, I'm talking about the derivative. If you know the power series for the original function, how do you get the power series for the derivative? The answer is you do the term by term derivative. So the statement is then the power series for f prime of x is f prime of x equals, you ready for this? The term by term derivative. It's that. You can just take this series, and inside the series, you take the derivative of each term. The derivative of x to the n, of course, is n times the derivative, or it's n times x to the n minus 1, right? That's how we do the derivative of x to the n. All right? This is a theorem because you might just say, like, isn't that just obvious? I take the derivative on the left side, I should also take the derivative on the right side. It's not entirely obvious that this is valid because that's an infinite sum and weird things can happen in infinite sums, but I would ask you to take my word for it. This actually is valid when you're working with power series. The power series for f prime of x is that, and also, you can also do this for the antiderivative. So I will say, and the power series for the antiderivative, not f prime, the power series of the antiderivative is similarly the antiderivative of the original power series, and that would look like Cn 1 over n plus 1 x to the n plus 1, right? That's the antiderivative of the power series terms. This is the term by term derivative and antiderivative. All right. And really, I should say this is just a technicality, but really it's sort of like a plus c, because every integral, every antiderivative might be different by a constant. And so it's actually, when you take an antiderivative, it may not straight up equal the antiderivatives of these because you might have to add a plus c or whatever. This is not very important, but should be in there for technicality reasons. All right, so this actually allows us to create new kinds of power series that look fairly different from the one that we started with. For example, starting with our favorite series, this one here, since that is true, I can do the derivative on both sides and get a new series for something else. So I'm going to do the derivatives on both sides. All right? Do the derivatives on both sides. Actually, this, because I'm going to do the derivative, it's more convenient. The left side, I am going to instead write like that, right? You could do the quotient rule on that, I guess, on the left side as written, or you could, to me, it's a little easier to turn it into this, write it this way on the left-hand side. So when I take the derivative of that, I get minus 1 minus x to the minus 2, and then the chain rule times negative 1, all right? That's the derivative of this. It's a chain rule. You move the exponent down, decrease the power by 1, and then the chain rule, I have to multiply times the derivative of the inside, like that. All right, and then on the right side of the equal sign, I take the derivative term by term of the series. X to the n becomes n x to the n minus 1. All right? Oh, sorry, can I squeeze in a few words to the theorem? I'm sorry. I forgot to say this is important, although we're not going to make a huge deal about this. Can you just squeeze this in on the side maybe? And, sorry about that, they have the same interval of convergence. I mean, remember, we always talk about what is the series and then also what is the convergence. If you do this term by term differentiation, it doesn't change the interval of convergence. That's all I'm saying. Sorry, I meant to say that before. I forgot. Anyway, this is a true series formula. Maybe we should just kind of like rearrange things a little bit. Just to write the left side a little nicer. This is, well, this minus and this minus cancel, right? I have a minus sign out front and a times negative 1 over here, so they can cancel. Really all this is, just writing it in a nicer way, is this. Like that, right? Yeah.
Would be parentheses.
Yeah, square, so, yeah, thanks. The square is outside the parentheses. That's not the same as what I wrote. Thank you. It's like that, all right? This is a real new power series. It's different from the one in the box, right? Basically everything we've talked about has been a variation of that one in the box. But this is really a different kind of power series, all right? Let's try a fancy one. How about, let's do the antiderivative. So you can get new series by starting with ones you already know and either taking the derivatives or taking the antiderivative. Let's do the antiderivative of the series for 1 over 1 plus x. All right. This one, if you do like we did, you would use that simple trick where you plug in a minus x instead of x. So that's the series formula for 1 over 1 plus x. We did this example, 20 minutes ago or whatever. I would like to do the antiderivative term by term on both sides. So on the left side, we're gonna have to do a little bit of work. The left-hand side is integral 1 over 1 plus x, right? What is that? Anybody know the appropriate integration strategy to use here? How would you do the integral 1 over 1 minus x? 1 over 1 plus x. We haven't done this in a while, but this is not an especially difficult integral to do. Yeah? You can do a u substitution. Call u the thing on the bottom. So u is 1 plus x, and then du is just dx. So this is integral 1 over u du, which would be, what is the integral 1 over u? Somebody shout it out. Yeah, it is ln of u in absolute value, I suppose. Okay, and then I should plug the original variable back in. This is ln of 1 plus x, like that. All right, so that's the left side. Really, I should put the plus c here, and we'll have to decide what the c is. I suppose we'll have to deal with the c. It's not a big deal. On the right side, it's not so hard to take the antiderivatives. The right-hand side is just minus 1 to the n, x to the n, right? This looks weird, but I'm doing the antiderivatives. Really, I should write the integral sign on the inside. I'm doing the antiderivatives term by term, right? But all I have in there is just x to the n. So it turns into x to the n plus 1 divided by n plus 1. So this, I'm going to get minus 1 to the n, and then 1 over n plus 1, x to the n plus 1. All right? So if we write this all together, the left-hand side is equal to the right-hand side. Those are the two antiderivatives on the left and also on the right, and they should be the same. So this is actually a great thing that we ended up with. What we have here is basically a series for the natural log, all right? This example looks completely different from all the other examples we've seen so far. This is a series for the natural log. Now, it's not a series for ln x. It's a series for ln of 1 plus x, which is a little weird, I suppose. Yeah?
Do I put a plus c next to the series?
You have to put a plus c somewhere. So I put it over here. Now, it's the same. If you put another constant over here, you could just subtract it onto this side and put them together. But yeah, it has to be on one or the other side. And actually, we should talk about that c. What actually is the c? Actually, you can figure out what the c is. What is the c? We can plug a specific value and actually calculate everything. Let's plug onto both sides. Anybody think of I'm thinking of a number I could plug in for x where I would actually be able to calculate everything on either side. We can choose whatever value you want to plug in. What do you say? 0. Yeah, I'm always going to go for 0 unless, sometimes like plugging in 1 is easiest. I would say plugging in 0 is the easiest thing to do here. If I plug in x equals 0 on both sides, hopefully then c will be left over as a variable and we can solve for it. So on both sides, I go left side ln 1 plus 0 plus c. I intend to figure out what the c is. And then on the right side, plugging in x equals 0. 1 over n plus 1, 0 to the n plus 1. All right? Can anybody say simplify on the right-hand side? What is that? You could show me on the fingers if you like. It's so simple that you can see it on the fingers. Yeah, it is. People are showing me this. It is 0 on the right-hand side. Everything, it's all a whole bunch of stuff, but it's always times 0 every time in the series. So the whole right-hand side is 0. On the left, I have ln of 1 plus 0. That's ln of 1. And what is ln of 1? It is also 0. They're showing me the signal again. All right, so that means c equals 0. All right. And so I'm going to write this for real now. This I'm going to put in a box somewhere. And I'm going to write it without the absolute value signs, and I will say a bit about that in a moment. But anyway, the formula is this. This is an important formula. It is the power series expression of the natural log. It is, to be more specific, the natural log of x plus 1. Unfortunately, it's not a power series for ln of x. It's a power series for ln of x plus 1. And since this one is so important, we should probably talk about the convergence. When does it converge? You have to kind of look back at what we've been doing this whole time. I used this, right? So this one right here, this one converged when absolute value minus x less than 1, because I got that by plugging negative x into the standard formula. But of course, absolute value minus x is the same as absolute value x, right? And then afterwards, all we did was take the antiderivative of that series. And as I said in green up here, taking the derivative or antiderivative does not change the interval of convergence. And so the convergence here is also converges when absolute value x less than 1, right? All right. Now this is the radius of convergence is 1. Remember, the interval of convergence, that means the interval should be between minus 1 and 1, although we don't know about the endpoints exactly. But anyway, yeah, I wanted to say a little something about this, ln of x plus 1. I got two things to say, actually. First of all, could we just write out what do these terms look like? ln of x plus 1, it is, if I were just to write this sort of term by term as a sum, starting with n equals 0, the first term is going to have a positive sign because it'll be minus 1 to the power 0, and then I get x to the 1 over 1. So actually the first term is just x. And then the next term, using n equals 1, it's a negative, and then x squared over 2. So this is minus x squared over 2. The next would be a plus x cubed over 3. This is what you get if you write it out. Minus x to the 4 over 4. So it's alternating, and it has n's in the denominator, right? This is a alternating series with n's in the denominator. And I have two interesting things to say about this. One is, check out what happens if you plug in x equals 1. If I plug x equals 1, now this is actually on the edge of this radius, and so actually it might not even converge here, it might diverge, but in fact, we will see something recognizable. If we plug in x equals 1, on the left side we get ln of 2, and on the right side we get, just put 1s everywhere for x, 1 minus a half plus, a half plus a third minus a fourth plus, etc. Anybody recognize that? This is that one weird example that I kept on telling you equals ln2, and I kept on saying we'll get there eventually. I like to explain why it actually equals ln of 2. This is why. This is the alternating harmonic series. We can show, it's easy to show using the alternating series test that it converges. What it actually converges to is not obvious, but this is how you would figure out what it converges to. It converges to the natural log of 2. All right. Anyway, this is an important formula. One other thing I wanted to say about this is that, and I'll put the convergence, absolute value x less than 1. Another thing to say about this is, wouldn't it be better if there was a formula just for ln x? Like, why does it have to be ln x plus 1? There's actually a reason for that, and I would say, so I want to just explain, unfortunately, there's not really a series for ln of x. Why not? I mean, ln just x, not x plus 1, but just x. Why not? It's because such a series, remember we've talked about power series, always has some interval of convergence. And since I'm writing the series like this, these are series centered at 0 that I'm writing here. So technically what I mean is there's not really a series for ln of x centered at 0. And the reason is because, actually, if you think about what the graph of ln x looks like, you will immediately realize that such a thing would not really be possible. It looks like this, right? And if I want a series centered at 0, it would have to have a radius, an interval of convergence like this, right? An open interval around the origin. But it's not possible for this series to converge near the origin because the function is not even continuous at 0. All right, that's why there's not really a series for ln of x centered at 0. This is because ln of x is not continuous. If I wanted to say more specifically, it's not continuous on any interval centered at 0. Right? Like the point 0 itself is a vertical asymptote. And so that's why actually there's no hope of making a series centered at 0 for ln of x. ln of x plus 1, though, is different. ln of x plus 1, where the plus 1 is on the inside, that means the whole picture is shifted to the left by 1. That's, if you recall your sort of graph transformation operations. ln of x plus 1 looks, actually, the graph of it looks like this. This is ln of x plus 1. This is ln of x, all right? And this one, you definitely can find a little interval around the origin where it's going to converge, right? That's why, for the sake of writing a series, actually ln of x plus 1 is a much nicer function to work with versus this one. There's really no hope of writing a series centered at 0 for that one. All right? Can we do one more example? And then I think that'll do it for us. Let's talk about, how about this? 1 over 1 plus x squared. This one, if I write the series like we did at the beginning, just using the simple tricks, this would be the series of negative x squared to the n, right? Just plug into the formula that we used at the beginning. And then if I sort of simplify a little bit, this is the sum, minus 1 to the n, x to the 2n. And then this one converges when absolute value negative x squared less than 1, but that's just the same as absolute value x less than 1. The minus in there doesn't matter because it's inside the absolute values, and then you can take a square root on both sides, and you just get that. All right. I would like to do the antiderivative of this series. So this is sort of the left-hand side, and that's the right-hand side. Let's do the term-by-term antiderivative and see what happens. On the right-hand side, that's maybe the easier one. I'm talking about inside the sum, I just do the antiderivative each time. This gives me a sum. I'm still going to have minus 1 to the n, but x to the 2n, you increase the power by 1, so it becomes x to the 2n plus 1, and then you divide by 2n plus 1. So this is 1 over 2n plus 1, x to the 2n plus 1, like that. All right. Okay, that's the right-hand side. What about the left-hand side? I'm talking about the antiderivative 1 over 1 plus x squared. Anybody recognize this? This is a bit of an obscure one. A deep cut, as they say. What do you think? What do you say? This is the arctan. Yeah, this is one of those inverse trig function formulas that, you know, if you did well on that quiz, you forgot about it since then. But this is, I will write as the arctan of x. And you got to put the plus c somewhere. That's that. All right? So actually what we have here, and these are equal. The right-hand side and the left-hand side are equal. So what we have here is actually a power series for the arctan, which is pretty cute, I would say. So that means, now I do need to talk about what's the c. But anyway, arctan of x, its series is minus 1 to the n, 1 over 2n plus 1, x to the 2n plus 1. All right? And again, I'm going to solve for the c by just trying to plug a specific convenient value in for x. And the most sensible one to try to plug in is just 0. Because when I plug in 0 for x, it makes the right-hand side terms all 0. So if I plug 0, come on now, plug in x equals 0, it says arctan 0 plus c equals, it's just a big sum of zeros, right? And what is the inverse tangent of 0? That is, what's the angle where the tan of something equals 0? I'm seeing the hand signals again. It is again 0. The arctan of 0 is 0. So this just says 0 plus c equals 0. So again, c is 0. That extra constant ended up not mattering at all. And so this is a true formula. Arctan x is this series. I'm going to sort of put this one in a box too. I would like to keep track of all of the important series formulas that we're able to come up with. And now this one, just because I always want to talk about the convergence here was this when we started, before taking the antiderivative. But then, again, taking the antiderivative does not change the interval of convergence. So that convergence interval is absolute value of x is less than 1. All right? Maybe I'll just put, let's just make a little list here. The other one you should know is ln of x plus 1. And this one, the formula was, these can be a little taxing to keep them straight, but it's that. All right? And then, of course, the simple one is this. All right? I know. These ones are the important power series formulas to remember. I got one more thing I want to say. We got to go in a moment. But check this out. I don't know if this, to me, this is profoundly weird. If I write terms of the natural log one, it looks like x minus 1/2 x squared plus 1/3 x to the 4 minus 1/5 x. What? I should be matching those numbers every time, right? Etc. What if I write out the terms of the arctan? Arctan of x is that formula at the top. Actually, it's almost the same. It's a first of all alternating sum here, but then this stuff here is really the same as that. Only this is going to be odd every time. It starts off as 1 when n is 0, then 3, then 5. So what we get here is x minus 1/3 x cubed plus 1/5 x to the 5 minus 1/7 x to the 7, etc. All right. What is interesting about this to me, I know it's time to go, but we're having a week off. Maybe you can just ponder this yourself. How crazy is it that the natural log and the arctan, they look almost the same to me. The difference is this one has all of them. This one has only the odd ones. All right? But why should to me, the natural log and arctan are not similar at all. They're just completely different functions. And they are used for completely different purposes, but their series are almost exactly the same. And it also makes me wonder, what are you going to get if you use only the even ones? Is it just like something else? I mean, is it, cosecant of x or something? Like, it could be anything, right? Why are these two things here so similar? It's crazy, in my opinion. Think about that. All right, have a great break. Do your homeworks before you go home.
Like, wouldn't it be so similar because they derive from a semi-similar equation?
Yeah, it's kind of because their derivatives are similar looking.
Yeah, because like 1 over 1 plus x versus 1 over 1 plus x squared.
Right. Yeah. Yeah. So I can explain why it's true, but it's still weird to me that
Yeah.
that they are so similar because they're completely different functions.
Yeah.